So dynamic range, generally defined as the ratio of maximum input level that the circuit can tolerate to the minimum input level at which the circuit provides a reasonable signal quality. So what dynamic range is actually, for example, if I have a receiver here, just put it in the black box and an antenna. So whatever signal that I receive here, just consider it as P in minimum signal that can give me enough output here that is detectable by whatever is coming outside after this receiver. And the dynamic range is the distance between P in minimum and P in maximum. So the maximum power that this receiver can handle. Generally, maximum power is defined by intermodulation products. For example, if I want my receiver to work nicely, then I want my intermodulation products to be as low as possible. So my receiver upper limit is generally when intermodulation products are just about to get a little bit more than my noise level. Then I normally consider that, okay, this is my this is the upper power limit of my receiver, and for the minimum power receiver is kind of the noise floor, for after which I will get nothing here. So I want my signal to be at least 3 dB above my noise floor at this point. That will define the lower limit, and the upper limit will be defined that whatever signal I get here is actually a clean signal, so it do not have interference from the neighboring channels, and the intermodulation product addition is as less as possible. So that will define my dynamic range. So generally, dynamic range of each receiver is different for different receivers. For example, the receiver in a mobile phone has a very high dynamic range because of a lot of technological advancement in the circuitry that we normally have in our mobile phones, and some other, for example, the journal FM radio receivers inside our cars have very low dynamic range because they don't want to be the purpose of those receivers is not as important as the purpose of our general cellular communication devices is. So the input power range over which the receiver is useful. Yeah, this is a very good definition, that the input power range level over which the receiver is useful is actually the dynamic range. So base the definition of the upper end of the dynamic range on the intermodulation behavior. Base the definition of lower end on sensitivity. So the upper end is actually defined by intermodulation behavior, and the lower end is actually defined by receiver sensitivity. Such a definition is called spurious free dynamic range. So if a spurious free dynamic range means the dynamic range of my receiver in which I will get a clean signal at the output of the receiver. Clean signal means it do not have noise, and it is actually at least 3 dB above noise, and it do not have interference from neighboring channels. So dynamic range, the upper end of dynamic range is defined as maximum input level in a two-tone test for which third order intermodulation product do not exceed the noise level. So we have already seen what IM3 is. So imagine I have two-tone signal omega 1, and let's put it as omega 3. So omega, so some of the products of omega 1 may cause interference in omega 3. So I want this input signal to be below noise level. So imagine my noise level is at this level, then the minimum power is when the signal is below this level. So I will just define my minimum and maximum based on this diagram here. So my minimum range is exactly this range, just above noise floor, and the maximum range is very high power, but when the intermodulation product is just below noise floor. So this is PIM, and this is actually P in. So this is the minimum limit, and this is kind of maximum limit. Okay, expressing all the quantities in dBm and using 20 log A, that is the amplitude, IP3, that is intercept point, third order intercept point at the input, and corresponding power at the input, or amplitude at the input, is equal to half of 20 log A omega 1 omega 2, that is the amplitude of my omega 1 and omega 2, that is the amplitude of my signals, that is this signal A, minus 20 log AIM3, that is AIM3, that is this level, plus 20 log A in. So A in is the power, is the amplitude of signal that is at the input. So P, in terms of power, PIIP3 is actually equal to P in plus P out minus PIM3 out divided by 2, where PIM out denotes the power of IP3 component at the output that we have just seen. Since P out is actually equal to P in plus G, if we talk about these values in dB, then this is true. Otherwise, generally P out is actually G into P in if we are talking about power in watts, and PIM out is actually PIM in plus G. Remember, we are working in dB that I have just mentioned, where G is the circuits. Let me just rub this. Okay, so where G is the circuit's power gain in dB and PIM in is the input referred level of the IP3 product. Having said that, we will have P intercept point, third order intercept point at the input will be equal to P in, that is the input power, plus P in minus PIM in divided by 2, which will eventually give me this equation. So if I rearrange, leave this P in here and move everything else on the other side of the of my equal sign, then my P in will be actually 2 IP3 at the input, that is I IP3 plus P intermodulation at the input divided by 3. So this value is generally what P in should be. Dynamic range. So the input level for which the IM product becomes equal to the noise level is thus given by P in maximum is equal to 2 PIIP3 plus MDS. So here I have just removed that intermodulation point with MDS. I want it to be below my minimum discernible signal level, that is definition of noise floor of my own system, that is just 3 dB above the actual noise floor, divided by 3, where MDS is actually noise floor plus 3 dB that I've just mentioned, where noise floor is minus 174 plus noise floor, noise figure of the receiver plus 10 log bandwidth in which we are operating. So the spurious free dynamic range is difference in dB between P in maximum and P in minimum. So I have actually tried to explain P in maximum, P in minimum at the start of 3 slides ago. So spurious free dynamic range is actually equals to 2P IP3 plus MDS. This MDS is actually moved, uh, uh, is replacing PIM intermodulation product power divided by 3 minus MDS plus signal to noise ratio, that is minimum signal to noise ratio at the output of the receiver, which will eventually give me this equation, that is 2 PIIP3 minus MDS divided by 3 minus signal to noise ratio. So for example, if a receiver has noise figure, let me try to draw a receiver here. So imagine the noise floor of this receiver is 9 dB, PIIP3 is minus 15 dBm, bandwidth is 20 kilohertz, required signal to noise ratio minimum at the output is 12, so signal to noise ratio required here is actually 12 dB. Then spurious free dynamic range using this equation will actually be 50.7. So it means minimum power level and maximum power level here, the difference between these two power levels will be almost 50.7 dBn. Sorry, dB, not dBm. 50.7 dB. So imagine our noise floor is at minus 150 dBm, then my receiver will actually work. Let's not make it minus 150, it's too low. Just imagine that dynamic that the minimum power level is at minus 100 dBm, then at minus 50 dBm the receiver will work nicely. After this, the receiver will not work nicely. It will have intermodulation product and interference. Below this value, I will just receive noise. So I just want my receiver to operate in this dynamic range. 50 dB is pretty big number. 50 dB is pretty big number. So if I make a receiver with 50 dB of spurious free dynamic range, it means I'm a good engineer. The SFDR represents the maximum relative level of interference that a receiver can tolerate while producing acceptable signal quality from a small input level. So here's a figure or a power level spectrum placed on a city floor, in which multiple colors represent different power levels that are received by mobile phone receivers. So imagine we have a base station antenna that is transmitting signal, and in this area we have a you can say a park zone in which we have multiple trees. Let me change the color. So this is kind of like with multiple trees. So our power is very low, our received power is very low. So if I check what red represents almost minus 115 dBm. dBm is the signal. So the minimum power here that I am getting is almost 105 dBm for receiver, and maximum value is almost minus 65. I am not seeing anywhere where I'm getting this kind of high power, but let's see this green area. Yeah, this may be an area. This area may be a place where I have base station is pretty close to this area. So that's why in this area I'm getting a power level of almost minus 85 dBm. So I am getting minus 85 dBm at one level, and perhaps there is some area where I am getting exactly minus 65. So my maximum value is minus 65 dBm, sorry. So my spurious free dynamic range is almost 105. 65 is 40 dB. So for this scenario of a city where a base station is transmitting a cellular technology signals, and our mobile phones actually receive those signals, if a mobile phone receive a signal of almost minus 105 dBm, it will still can make sense out of signal because it will be above noise level. And if a signal is very high, that is at minus 65 dBm level, then still my receiver will be able to get enough signal without getting an interference from neighboring base station. So that is also extremely important, that interference should the neighboring channels should not interfere with my signal. So for example, if I am using a mobile phone and there is another person close to me using another mobile phone, if the power that is radiated by the base station is too high, then there is a possibility that my information can go as interference in his cell phone, and his information can go in my cell phone if we both are operating on neighboring channels. That's also important if we are operating in neighboring channels. So all these things are extremely important if you're radio frequency engineers, and perhaps you will be able to define or design some of these systems. So this is one example of Huawei 1+1 passive plus active 5G antenna combination. This is kind of a base station that is providing similar coverage on a city or in park area plus some other buildings, and the spurious free dynamic range of mobile phones are actually defined by the radiated power by these base stations, and we want all of our base stations to cover maximum portion inside the city with almost no shadow zones where signal is enough that it lies within the space free dynamic range of every mobile phone present in that area. So this is an example of coverage area of 5G in Belfast. So uh, this reddish area here represents places where 5G signal is enough. So the power radiated by 5G base stations is enough that if we have mobile phone can that can receive 5G signal can work well. So this is kind of a map of Belfast. So for 4G, I think this green shaded area is for 4G, and for 3G, I think this uh, light green area represents the availability of signal of 3G. So you can see that 5G is covered almost majority of Belfast area. Also a good portion inside our sea where ferries go to either Liverpool or Scotland. So 5G is kind of covering a good area in Belfast, but there is one important note that currently whatever is launched in the name of 5G is sub 6 gigahertz 5G. Millimeter wave 5G is yet to be deployed. So millimeter wave 5G is the next thing that we are looking at, and I work on radio frequency systems that operate on millimeter wave 5G. So perhaps some of the work that we do will be a part of millimeter wave 5G in near future. So thank you very much for listening. So just to review, in the second set of handouts that I've shared with you, we have covered gain compression, 1 dB compression point, intermodulation distortion, third order intercept point, sensitivity, and dynamic range. So minimum level of our signal is generally defined by noise floor or minimum discernible signal, that is ideal noise floor for our receivers, and the maximum power is dictated by either 1 dB compression point of any of device, either amplifier or a mixer inside our receiver, or by intermodulation distortion points. We do not want intermodulation distortion. We do not want our amplifier to operate at a saturation level. We want them to operate at a high gain level where they can actually give us a gain value, and that is kind of a definition of maximum power level and minimum power level of our receivers. And thank you very much for listening.